Welcome and hello to the iSystem webinar series. Today's episode is about timing analysis using the iSystem Profiler. Discovering the possibilities means that we provide an overview about the various features of the iSystem Trace Analyzer for timing analysis purposes, a basic understanding how a profiler tool works and what it can do for you. My name is Sabrina Kistlinger, I'm the moderator. Today's speaker is Armin Stingl, who will lead you through the technical presentation. Armin is Senior Systems Engineer at iSystem and the Product Manager of the iSystem Trace Analyzer. In addition, he coordinates the cooperation activities with AUTOSAR and OS vendors, as well as with other timing analysis tool vendors. He is also a member of the AUTOSAR working group resources dealing with timing analysis concepts for AUTOSAR Classic and Adaptive. Before we start, I would like to give you some general information. During the webinar, you will be muted. If you have questions, please use the question tab in the menu bar. Below the question tab, the handout tab allows you to download the presentation. Today's episode will be recorded and published on the iSystem YouTube channel. And at the end of the webinar, some of your questions will be picked and answered by Armin. All others will be answered afterwards by email. So let's start, Armin. Over to you.
Welcome to this webinar also from my side. You may have noticed that we have subtitled this webinar, Discover the Possibilities. This means that I want to give you an overview of the various features of the winIDEA Trace Analyzer for the purpose of timing analysis. I will not go into the details for each feature. The idea is that you get a rough understanding of the winIDEA Profiler capabilities in order to maybe trigger some ideas in your head about how you could utilize these features for your particular timing analysis use case. Looking at the agenda, I will start with a quick comparison between different classes or maybe concepts of timing analysis. And once you know which concepts are used by the iSystem winIDEA Profiler, I will explain the building blocks of our profiler. We'll also give you a quick introduction into hardware trace. Once we have this basic understanding, we can dive deeper into specific features and use cases, like the profiling of an AUTOSAR operating system. Then we'll take a closer look into function profiling. Here we'll cover both fundamental options for function profiling, meaning function profiling based on program trace, as well as function profiling based on function entry-exit instrumentation. The next topic will be our so-called profiler inspectors. This is a rather special and also quite advanced topic, but I want to mention it here in this webinar for you to roughly understand the timing analysis capabilities offered by these inspectors. As a last agenda item, I want to present a new feature of the winIDEA Profiler, the possibility to do timing analysis by means of sampling via the debug interface instead of hardware trace. So as an introduction to the whole topic, I want to give an overview about the various concepts, how you could do timing analysis in an embedded system. In my opinion, there are three fundamental concepts of timing analysis. First, a purely statistical analysis based on sampling certain objects within your software. Then you could do some measurement, either on-chip or off-chip. Off-chip would be, for instance, maybe that you toggle a pin and measure timing with an oscilloscope. On-chip measurement can either be done by utilizing some dedicated hardware, such as a core performance counter, or also using some generic counters. But in any case, this approach requires an instrumentation of the code, meaning dedicated software needs to be added to the actual software to be analyzed in order to control the measurement hardware. But at least this approach yields exact and reliable results. The third approach is based on trace. And as this figure indicates, trace-based timing analysis provides the maximum of information and thus also the maximum of analysis options. And it also includes all the analysis options offered by the other two classes, measurement and sampling. The unique thing about trace is that it allows an exact reconstruction of sequences of various events over time. From this information, you can derive a complete set of timing metrics And you can analyze CPU load over time, analyze event chains, and function call sequences. So basically, it provides you full insight into the software execution. From measurement, you basically get exact timing information of things like functions or as tasks by measuring the time between entry and exit. From this, you can drive min, max, average metrics and calculate CPU utilization. But you cannot analyze, for instance, function call sequences or event chains. From sampling, you can only get statistical results, meaning distributions and utilizations. The results are basically only approximations of the reality, because with sampling, there is no guarantee that really all relevant events have actually been captured, meaning the more data is sampled, the more accurate can be the result. The classes trace and sampling are drawn in blue, because these are the concepts which can be used with the iSystem profiler. And speaking about profiler, what exactly is a profiler? I'm trying to explain this in the next slide. So with this slide, I'm trying to explain the profiler by looking at its building blocks. The profiler basically operates in three stages: the recording or capturing of data from the target, the analysis of the data, and the visualization of the results. Data can be obtained from the processor either form of trace data, typically captured from a dedicated trace interface, or it can also be sampled, meaning read out from a processor via a debug interface. The sampling-based profiling is actually a pretty new feature of our profile. I will come to that in more details later on towards the end of the webinar. One type of trace information is instruction or program flow trace. Program flow trace is basically informs the tool about discontinuities in the software execution, something like jumps or branches. And based on this, the tool can reconstruct the entire program flow, including time information, down to each individual executed instruction. In the analysis stage, the tool can derive a complete profile of all functions and finally display the results both in form of a timeline, meaning the function execution sequence over time, and in form of a listing of all sorts of statistical information like min, max, runtime of average CPU utilization of a certain function. The other type of trace information is based on data trace, meaning the trace hardware in the chip captures the data right to specific locations and sends this data out to the tool, along again with some timing information. By knowing how to interpret the data written to the specific locations, the profiler can derive various types of information from this. The data written could, for instance, be used to mark the entry and exits of specific functions. So this is used for function profiling. Or the data is written by the OS scheduler and tells the profiler which OS task is currently running. This is typically the approach for tracing the running task of an AUTOSAR OS based on the so-called ORT file. Or there is no further interpretation needed at all, so plain data profiling is done. For a proper interpretation of the captured data, the profiler in some cases, for example function or OS task profiling, needs additional information. This can be provided either via some sort of OS-specific plugin, for instance the reading of an AUTOSAR ORT file, or via the iSystem-specific XML file. And also an optional extension of the analysis stage, there are also the so-called profiler inspectors. I just want to mention it here briefly, just to understand later on in the webinar where this feature belongs to. In this slide, I quickly want to give you a basic understanding about hardware trace, just to make sure we cover the entire trace chain. So the data is generated by dedicated trace hardware in the chip. This hardware is closely coupled to the core. The program trace logic captures program flow discontinuities like branches and function calls as mentioned. The data trace logic captures data writes to specific user-defined locations. The instrumentation trace is actually a special form of data trace, but the trace data generation is supported by some sort of instrumentation code. For example, On ARM Cortex-M based devices, the relevant data can be written to a so-called stimulus port of an instrumentation trace module, which then produces a dedicated trace message. All these trace messages are output via some sort of trace interface. Some processors also attach a timestamp to these trace messages. Alternatively, the timestamp can be added to the trace message by the trace recorder, like the iSystem blue box, when captured from the trace interface. The blue box may buffer the trace data and finally forwards the data to the PC running the winIDEA profiler. So now I guess we have the technical foundation to do the next step and actually perform a timing analysis. The kind of objects we are interested in terms of timing analysis, I think, are functions, OS tasks and interrupts, data, and maybe also a network attached to the target. On the left-hand side, we see a sample profiling result including all the types of objects we are interested in. On the top, we see the functions. In the middle, the OS, and also one data object. And on the bottom, we also have included a trace recording of a CAN bus communication into the profile timeline. And of course, all these objects are synchronized in time to each other. Just as a note, this webinar we will not further discuss network tracing, but we do have dedicated trainings and webinars on these topics as well. As the first step, we are looking at the operating system. Also from a technical point of view, it does actually make sense looking at the OS first, because measuring specific timing parameters also on functions does require that the profile is aware of the OS context switches. On the left-hand side, we see a sample profiling result including a timeline and statistics of all types of objects we're interested in, meaning OS tasks, ISRs, and also functions. And as you see here, runnables instead of functions, obviously we will focus here more on AUTOSAR OSs, but the same principles also apply more or less to any other preemptive real-time operating system. The screenshot that you see here is actually taken from an AUTOSAR demo using the ETAS RTA OS, running on an NXP S30K148 microcontroller. So how do we get to such an AUTOSAR profiling? Here I quickly want to demonstrate two options. The first option is the easy one and pretty much the standard way of doing AUTOSAR profiling these days. This is running task and ISR profiling by means of the so-called ORTI file. Here I have a winIDEA workspace running this little AUTOSAR demo on the S30K148 microcontroller. So if I want to do running task and ISR profiling, I need to import the ORTI file into the winIDEA. The ORTI file is generated by the AUTOSAR OS generation tool. So via the debug menu, I can define the corresponding symbol file and also the underlying OS. Here in our case, we have an AUTOSAR OS, so I select AUTOSAR. And the OS is described in form of an ORTI file. Here the file pizzapronto.ort. So I do a new download. Then start the trace recording and also start the CPU. Then the profiler builds up into the timeline and also the statistics. Okay, so let's take a quick look into the profiler configuration first. We see the profiling analysis is selected for code, meaning function profiling based on program trace, and for the OS. And for the OS, we have selected that we want to analyze tasks and ISRs category 2. And if you, for example, select tasks here, the profiler shows us the information it has taken from the ORTI file. For example, this ORTI running task object can be analyzed by tracing all data writes of the OS kernel to the variable OS running task. But as the name implies, we can only see which task is currently running. So let's take a closer look at the timeline. So we see this task write code is running for a while here. Then this task order pizza is running, write code again, eat pizza, and then finally write code again. But actually looking at this pattern, I think we kind of guess that's what is really happening here, because in reality the write code task is started here, gets preempted by order pizza, write code resumes, gets again preempted by eat pizza, and then finally terminates. But we cannot really measure this, and therefore for the profiler all these pieces here are treated as multiple instances of the task write code. And all the statistics is of course calculated accordingly. Like the net time here, for example, is okay. But with gross time, you need to be a bit careful. It only takes into account task preemptions by ISRs, but not preemptions by other tasks, since we cannot measure this, obviously. Analyzing the CPU load is possible. However, only if you actually have a real idle task in your system, where the CPU is actually idling. In this case here, the idle task net time is roughly like 33%, meaning the CPU load is 100% minus 33 equals to 67% CPU load. But overall, this is not really the ideal profiling result. It would be much more informative if you could see each detailed task state. And how to do this, I will show you now. So I'm opening a new winIDEA workspace, and I'm just using the exact same demo code again, just another winIDEA workspace. And I'm adding the AUTOSAR awareness to the winIDEA again. But here, instead of the ORT file, I select this iSystem XML. Here I actually don't want to go into details about this XML file. I just want to mention that the file can actually be generated automatically by a utility called ITCHI, which stands for iSystem Trace Configuration Helper. And we also have dedicated webinars and application notes about this topic. So if you take a closer look now at the timeline, we now see all the detailed task dates. So how did we do this? The XML file is actually just one part of this game. And I have to admit that the whole solution actually depends on the particular OS. But here in this case of the ETAS RTA OS, the main magic is actually done in the profiler inspectors. And I also don't want to go into details here, but it's just so much. The inspectors basically calculate the task states from multiple different status data from the OS. So let's take a look at one of the inspectors. So we basically trace multiple data objects and evaluate them according to this expression here. And the result of this expression controls this state machine representing the task states. So with this method, now we clearly see what happens. The write code task is first suspended and gets activated, entering steady states for a little while before it becomes running. Gets preempted by order pizza, so it goes to ready state, resumes again, and again preempted by the eat pizza, and finally it terminates. And by the way, part of the XML is also that you can define certain functions to be treated as runnables. They will then be listed here separately, and they can also be included, for instance, in a BTF export when you want to export the profiler timeline to another timing analysis tool. Okay, so now we have a basic understanding of the OS profiling. So we can move one step further and discuss function profiling. And as mentioned earlier, there are two fundamental concepts for function profiling. One is instruction or program flow trace. This does not require any modification in the code and is completely non-intrusive, as it is entirely handled by the on-chip trace hardware. The approach is, as indicated here, that specific trace messages are emitted by the chip whenever there is a program flow discontinuity, like branches or returns. Based on this information, the trace tool can reconstruct the program flow down to each individual executed instruction. This is very nice, but the downside is that it produces quite a large amount of trace data, and especially in multi-core applications, this may result into trace overflow. And you need to keep in mind, for runtime analysis of functions, I'm not really interested in what's happening inside this function. So an alternative concept here is to use for this particular function profiling use case is to use code instrumentation in conjunction with some sort of data tracing. And in this concept, we use a write access to some traceable object like a global variable or a dedicated instrumentation trace hardware like the ARM ITM module to generate a data trace message. Such a trace message needs to be generated on entry, on and on exit of the function, like depicted here. Next, I want to take a closer look into the function profiling statistics, meaning on some basic function timing parameters measured by the iSystem profiler. For this, we are looking at such an example here. Here, this runnable R3 calls various subfunctions like function 1, function 2, and so forth, and also it gets preempted by an ISR category 2. Based on this example, I want to explain the timing parameters net time, gross time, and call time. The first one is net time. It is often also called the core execution time. This is the time the core really spends in executing the function body of the function, here of this runnable R3. So it does not include the time in any of the subfunctions or interrupts, or also tasks which may interrupt this function. Next is the gross time. This is the time between entry and exit inside the current OS context. So here the gross time includes the time in the runnable itself, including all its subfunctions here, but excluding the time in this ISR2, which preempts this runnable. Since the ISR2 is a different OS context, but also a preemption by another task would be a context switch. And finally, the call time. This is simply the time between function entry and exit, including all subfunctions and preemptions, maybe by an ISR or some higher priority task. In AUTOSAR terms, for example, in a timex execution time constraint, this would also be called a runnable response time. Okay, so unfortunately a bit more theory, but I think it is needed to really understand how function profiling works. In this slide, I want to give you a bit more insight into various function profiling methods. Here we can distinguish two basic types of analysis, the flat analysis and the nested analysis. The flat analysis is a rather simple type of analysis. Based on the reconstructed program flow, the flat analysis looks basically at the address of each instruction, and if the address falls within the address range of a certain function, the execution time of that instruction is taken into account for this function. So it only detects which function is active at which time. It does not recognize any relationship between the functions. However, the advantage of this flat analysis, it is not really affected by any sort of compiler optimizations, and therefore flat gives you really a rather robust and reliable result. On the other hand, you have the nested analysis. As the name implies, it recognizes also function nesting. This type of analysis can be done in two different profile operating modes, either entry-exit or the so-called range mode. The exit mode explicitly tries to identify function calls and returns and builds up a function call stack from this. However, this mode relies on the assumption that dedicated function call and return instructions are actually used by the compiler. This may not always be the case for every function due to instruction set architecture or maybe also compiler optimizations. But this type of analysis is used when function profiling is not based on program trace, but done via instrumentation trace. Because in this case, the function entry and exit are clearly marked by instrumentation code and data trace. So in order to overcome these limitations, we also have this range mode, which is a mix of entry-exit and flat mode. It performs an instruction address comparison like a flat mode, but also adds algorithms for detecting function calls and returns. And you're trying to take into account many types of compiler optimizations like function tail merging and others. So this requires really some heavy code analysis and deep knowledge of the optimization schemes of various compilers. And a while back, we actually introduced another type of analysis, the call stack analysis. When this mode is enabled, in addition to range or entry exit, we list all the detected function call sequences in the timeline and also in the statistics view. I will show an example later on in winIDEA. Okay, so first take a look at the range mode, since this is the mode which is also the default mode in winIDEA. As said, it recognizes function nesting. It requires that the OS context switches are also traced, and the profiler builds up a function call stack for each of those contexts. This also means in case you maybe have a short trace overflow, the profiling analysis needs to be aborted, as the function call sequence may now be broken. The entry-exit mode has pretty much the same properties. The only special thing here is that it is used especially in the case of function profiling via instrumentation, as mentioned. So now we come to the flat mode. And as a reference, I also copied here the profiling result of the range mode. And as you can see, the flat mode profile is really a completely different thing. Here the profiler doesn't really know that all this here, this is all one instance of the same runnable R3 with subfunction calls. In flat mode, the profiler handles all these three sections here of runnable 3 as completely separate instances of this runnable. And this also means that the timing parameter calculation is based on this artifact, so the result may be interpreted differently. Yeah, the total net time, for example, is of course the same, but all the other parameters, they may actually differ. Okay, the next two topics, call stack analysis and inspectors, I would rather demonstrate to you in winIDEA itself. Guess we have seen enough slides by now. So this workspace is already set up for task state profiling. The AUTOSAR OS used in this example is an Electrobit Trezor Safety OS running on an Aurix TC39 device. And it communicates with another microcontroller via a CAN bus. So let's take a look first at the profiler configuration again. The profiler is set up for code profiling, meaning function profiling via program trace, OS profiling, and in this case, here also network tracing, meaning CAN bus tracing. The code profiling is done in range mode, and also here the call stack analysis is enabled. So I'm running a trace recording. On the bottom, you see the CAN frames, the OS in the middle, and functions on the top. So what's happening here is the other controller sends a CAN frame called the master request, and this device responds with a slave acknowledge frame. So if you follow the whole event chain, we receive the master request frame. This triggers a CAN ISR, and the ISR activates the RT event task, which calls the modify echo runnable and also the send signal function for sending back the slave acknowledge frame. And by the way, the slave acknowledge frame here is sent this late because the CAN bus is occupied by another frame during that time here. Okay, first we want to take a look at the call stack. And as you can see here, there are of course a large number of function call trees detected. So an important feature here is the filtering. Here I'm interested in these two functions, the modify echo runnable and the send signal function. And for the filtering, we cannot simply use a plain function name filter applied to all listed function names and in all call tree levels. This will potentially break displaying the complete call tree, as some function within this call tree may be masked out. So let's set a filter for modify echo and for send signal. And for instance, if we look at the function comSendSignal, it does not seem to call any further subfunctions. But in fact, they're just not displayed, meaning they're masked out by the filter as the function name filtering is currently applied to the call stack levels. So this doesn't seem to be practical here. What we want instead is that the filtering is only applied to the top node of the call tree. It's only the root function of each call tree. And we can specify this via the filters option and by selecting filter only first level items. So now we can inspect the entire call tree of this root function here. So basically, the timeline visualizes the function call sequence and nesting levels over time. And the statistics view lists the exact timing numbers for each function in the call tree. And you can easily see how much time each function contributes to the overall call stack, and especially when looking at the cross time. Okay, so these were the basics about call tree analysis. Now a bit more on the profiler inspectors. As a showcase, we take this RT event task. And as a use case, you want to check if the task ever exceeds a certain response time constraint. So how can we do this? As you can see, the profiler already analyzes the exact OS task states. Here, idle, new, ready, and running. And as a first step, we create an inspector which measures the response time of the task, meaning the time from activation, in this case the state new, until the task termination. So the basic concept of this inspector is that these two events of the profiler, a task activate event and the task terminate event, control this state machine here. And for instance, an activate event will change the state from default to response time, and while the state is response time, we see this red bar here in the profiler timeline. So this basically creates a new profiler object which shows the response time of this task. And in a similar fashion, we have also an inspector here to show the initial pending time of a task, meaning the time between activation and running. But for our use case, the next step, we have to add another inspector which creates an object which is active, meaning red, as long as the response time is within the set timing constraints. And another object which is active as soon as these constraints have been exceeded, so violated. So here we see a couple of violations. And if, for example, you want to further analyze what happened around the maximum violation, we can utilize our profiler properties dialog for this violation object to navigate to exact this location. So apparently, in this case, the RT event task got preempted here and therefore could not meet the response time constraints anymore. Okay, how does this time constraint inspector now look like? Here we have again a couple of events controlling the state machine, and in addition, we also specify a time constraint here. So basically, generating an event in case the response time exceeds these 28.2 microseconds. Okay, this was it about call stack and also inspectors. Now I come to the last topic of this webinar. Here I'm basically showing a new feature of the profiler which will be released in the near future, the sampling-based profiling. The big difference here compared to the previously discussed profiling concepts is that the analysis is not based on data captured from any sort of trace interface. Here the data is obtained by sampling specific memory locations or the CPU program counter, meaning the debugger reads out these objects via the debug interface. So the obvious advantage is that this approach does not require any dedicated trace hardware, such as special emulation devices or trace adapters. But, just to make this clear, the idea here is not to replace a real trace analysis, because the artifact of the sampling-based approach is that it is not guaranteed that all relevant events can actually be captured. I cannot really go into details now regarding the exact sampling mechanisms, but it should be clear that this concept is mainly used for statistic analysis or for sampling rather slowly changing variables in your system. But we try to get the maximum out of this feature, so we implemented dedicated support for the following 3 use cases. The first use case is a function load analysis. So by sampling the PC, the program counter, the profiler calculates how the CPU load is distributed across all executed functions. The result is basically a CPU utilization as a percentage number for each function. The load distribution is both reported based on all taken samples in the statistics view, but also as a function load over time in the profiler timeline view. Here for the timeline, a sliding window averaging approach is used, which calculates the load within this time window across the PC samples taken within this window. The second use case works in a similar fashion, but instead of the PC, here we sample the OS running task and running ISR variables. So the result is an OS task and ISR load distribution. The display is again a statistics across all samples and also as a load distribution over time. So the idea for these 2 use cases is that you run the sampling for a relatively long time until you see the statistic numbers kind of stabilize. This measurement may not be 100% exact measurement, but it gives you a very good indication about the load situation in your system. And this should allow you to judge if your application is running correctly or not. The third use case is a completely different one, and it's actually not really related to timing analysis, but anyways. Basically, the idea here is to build kind of an oscilloscope for data signals in your system. The main intention here is to monitor a data signal over time. This use case has been available for quite a long time already, but not internally in the profiler, but via an external tool called winIDEA. Okay, since we do have some time left, I can quickly demo the new sampling-based profiling. I want to focus on the 2 use cases, function load profiling and OS load profiling. Here we have again the AUTOSAR sample running on this SWK148 micro, the same sample as I have already used in the first part of the webinar. First, we want to look at the function profiling by means of PC sampling. So here I have already created analyzer configuration. The profiler is actually set for data profiling in this case. And in the data profiler area, when creating a new area, you can now actually select how the data should be acquired, either via trace, via real-time data acquisition, so the data sampling, or via PC sampling. So we select PC sampling here and give the area some descriptive name, like for instance function load. Now when we run the PC sampling for some reasonable time to get some good statistics, okay, so on the timeline we now have the function load over time using the sliding window approach. So when moving the cursor, it gives you the function load in this particular time window. The statistics show on the top the total number of sampled PC values and how many of those samples can be assigned to the individual functions. And you can also sort the functions according to the count values. Next, we look at the OS load profiling. So we switch to another analyzer configuration. Here we have also set the profiler for data profiling, but when creating a new profiler area, we now select real-time data acquisition. And we actually do this for both the running task variable and also for the running ISR variable. So let's take a closer look at the running task area. Here, the tool actually allows us to specify the sampling interval. A 0 here means that the blue box samples the object as fast as possible. But I can also define a specific sampling rate, like for instance 1 millisecond. Okay, run the sampling again. Okay, so we get again the CPU load over time. Of course, now it is the west task and interrupt load. And the statistics view, we get the overload for each task in ISR based on all the taken samples. And for instance, if you remember from the demo at the beginning of the webinar, when using trace, we measured a CPU load of about 67% based on the idle task load of these 33%. And here we pretty much get the same numbers. Yes, so this concludes the webinar about timing analysis using the iSystem Profiler. I hope we could give you a good overview about the possibilities, although I could, of course, not cover all the features of our profiler. But I do hope that some of these features can also help you to realize some of your timing analysis use cases. In the next 5 minutes or so, we try to answer some of your questions that you have sent in via the webinar chat.
Thank you, Armin, for your detailed presentation. As you already mentioned, let's continue with the Q&A session. Several questions reached us, but we'd like to pick quite different ones. The first question is about sampling-based profiling feature. Does the sampling-based profiling feature require a trace license?
No, it does not require a trace license. So the regular debug license is good enough for this type of profiling. But you have to be aware that not all CPUs are supporting this mode. But we do, for example, support ARM, Cortex M and A cores, and also like the Infineon Tricore, for example, are supported. But there's also another limitation. This way of profiling, sample-based profiling, is only available on the IC5700 blue box.
Thanks, Armin. Another one is about automation. Is it possible to automate the timing analysis by the iSystem Profiler? We want to include timing checks into our continuous integration setup.
Yes, this is certainly possible. We have a pretty comprehensive winIDEA API. So in our native scripting language is Python. And via this API, you have access to basically all profiler results. Using Python, you can do all kinds of post-processing of the results, and you can also, for instance, generate a Jenkins JUnit XML file. So with Python, you're rather flexible on that end. And for example, integration with Jenkins is quite easy then to establish.
Thanks again. And another one refers to a specific slide. One of the slides about profiler operating modes mentioned the mode call side. What's that?
Yeah, this is a really special profiling mode, which is only relevant in specific situations, especially when you want to do function profiling, but the trace bandwidth of your particular device is not capable enough to do like a continuous program flow trace or active all the time. And on processors which actually allow to limit the program trace generation for specific address ranges, then you could, for instance, do the following. In the use cases, for example, like this, you want to profile runnables, and you know that these runnables are directly called from within specific task function bodies. Then you would limit the program flow trace to those task function bodies only for these address ranges. And then the analyzer will just analyze which functions are called from this address range, from this function body, and also return to this again. So this task would then be this call site. And yeah, this allows, for example, to do run-level profiling also with limited trace bandwidths. But I said it's only available on or usable for controls which allow this limitation of programmable trace to address ranges. But for instance, on a Tricore and Aurix device, this can be used, but also on some higher-end Cortex M7 devices, for example. These are some typical targets for this application.
Thanks, Armin, for clarifying that. And there are a lot of questions which reached us and are left at the moment, but slowly we need to come to an end. And before you leave, I would like to give you some additional information. Don't forget to download the presentation in the handout tab of the menu bar. Check out our free online trace tutorial, our various application notes, and our YouTube channel, where this webinar will be hosted later on. And if you want to, feel free to register for our newsletter to get updates automatically. If questions come to your mind later, feel free to send an email to webinar@isystem.com. Thanks for attending, and please fill in the feedback form after leaving. See you next time when we are talking about code coverage, how to avoid dead code. Bye and take care.